Okay, how's everybody doing? I wanted to complete part one of the titration video. I'm going to pick up where we left off. We left off with the titration of HF, a weak acid, with sodium hydroxide, a strong base, to create water, and NaF, excuse me. Okay, so remember, NaF is a salt, but that salt is aqueous, and F minus is a weak base because it is in fact the conjugate. Okay, so what does that mean? That means that after we look at the stoichiometry and determine the limiting reagent, which is done in the earlier video, part one, then we are left with the in solution equilibrium that's going to be started with HF and F as the acid and conjugate base pair. What you saw in the first video is me using ice table and then set up the ice table using Ka, solving for H3O plus. Now, one thing that I had not done at that point is I had not placed our point on the graph, and so I've done so. From that method, we saw a pH that was equal to roughly about 3.18 or 3.2. And now I wanted to show you, now that we've learned buffers and how to use Henderson-Hasselbalch, this process you can skip the ice table if you are before equivalence. Okay, so you can use Henderson-Hasselbalch before the equivalence point, right? You can use Henderson-Hasselbalch before the equivalence point, but you cannot use it at or after in a situation such as this. So weak acid titrated with strong base, before equivalence you can use Henderson-Hasselbalch. Why? Because remember, Henderson-Hasselbalch is conjugate base over acid concentration, and since we are halfway to the equivalence point, the halfway to the equivalence point, pH is equal to pKa. Why? Because this log goes to 0, log of 1, and we're left with pH is equal to negative log of 6.6 times 10 to the negative 4. Now, if you notice on the reference material, in that video I use this value in the reference material. I think it's very similar, 6.8. Again, utilize whatever reference material you have here, and now we end up with a pH that's equal to 3.18 if you plug this in the calculator and verify. Right, 3.18. So, as we say, two different ways to skin a cat. Ice table is always going to work. Always going to work. We drop the X here because of a small Ka versus the concentration, and we can also use Henderson-Hasselbalch if we are before equivalence. Okay, before equivalence. So we have our first point on the graph, which is the halfway point. Now let's take a look at the situation at equivalence. So I'm going to erase this. And I'm working in a little bit smaller space, but I do have the camera, so you should be able to see this. Okay, if we work at, I think we were looking at 0.1 molar and 0.1 molar of each of these. Let me verify that. And let's look at 100 milliliters of both. So if we're dealing with 100 milliliters of both, then we are looking at the stoichiometry. So I was trying to be consistent with the table. So if we're talking about before limiting reagent and after, to be consistent, before we are starting with 0.01 moles, and here we have 0.01 moles. So now we are at the equivalence point. Why? Because the number of moles are equal. The limiting reagent is in fact 0.01. So we are subtracting that, and afterwards we are left with none of these. Remember, we never worry about water. And here we have 0 plus 0.01, and at equivalence, or after the titration, we are left with 0.01 moles of F minus. Right? So I wanted to show you how you could use the table in the titration. But now, again, because we have F minus, which is a weak base, in solution in a new volume. How do we know it's a new volume? Because we have to add these volumes. Remember, volumes are additive in the titration. We now have the concentration of F minus is equal to 0.01 moles all over 0.2 liters. Okay, 0.2 liters. So now this is going to be equal to 0.005 molar. Excuse me, 0.5, sorry. So now we know the concentration of F minus. Because we are now at equivalence and we have neutralized all of our acid, right? We have neutralized all of our analyte. We are now left with the byproduct, which is the conjugate base, which does have a basic interaction with water. So now we are dealing with F minus plus water to give us HF plus OH minus. This is not a scenario where you can use Henderson-Hasselbalch. You can't use HH. Why? You can't, because this is not a buffer anymore. We are now dealing with one species in solution that is going to achieve equilibrium at some point. So what do we do here? Now we must use ice. We are dealing with 0.05. We don't worry about water. We assume that we have none of these. We assume that we're going to create acid. Why? Because this is a weak base. And we have an ice table. Now, very important. Very important once you complete the ice table to recognize, very important to recognize that we are now dealing with F minus, which is not HF, which means that we need to find the KB. So if we know the Ka is 6.6 times 10 to the negative 4, then we know that Kb is equal to Kw over Ka. So therefore Kb is equal to 1 e to the negative 14 divided by 6.6 e to the negative 4. We're dealing with 1.52 times 10 to the negative 11 is our new Kb. So this is what we utilize here in our Kb expression. Remember, Kb is equal to F minus OH minus all over, excuse me, HF OH minus all over F minus. And be sure that you recognize immediately that since you're dealing with a base reaction of equilibrium of a weak base, you're using Kb. If you're dealing with an acid, you use Ka. Now that we know the value for Kb, we know what to plug in from our expression here. We can take a look and we can just see that Kb and concentration are hugely different, so we can drop x. So now we're left with x squared over 0.05 is equal to Kb, which means that we can solve for x using our algebra, and x is equal to square root 8.7 times 10 to the negative 7, and this is equal to hydroxide concentration. But we cannot get the pH directly from this. We need the pH from hydronium, so we can use POH is equal to negative log of OH minus. And we can determine that POH is equal to 6.06, and therefore the pH is equal to 7.94. pH is equal to 7.94 at equivalence. Slightly basic. Slightly basic because the weak base F exists in solution. Mostly exists in solution. So 7.94, which is roughly 8. Six, 7, 7, 8. So there's our next point on our titration graph, right? Our next point on our titration graph. So this is at equivalence. A couple different things just to remember. You must do the stoichiometry, and I'm using this to do the stoichiometry. You then must determine concentrations of the species of interest, which is the conjugate base, and then you must do ice table. You cannot use Henderson-Hasselbalch in this situation. At equivalence or beyond, no Henderson-Hasselbalch. Only before equivalence and using in buffers. Okay, so now we have the point at equivalence, and then the last thing that we like to do is we like to look at after equivalence. So, if we take a look after equivalence, we said what happens when we add 200 milliliters of titrant at 0.1 molar. Now we're dealing with 0.01 moles, and here we're dealing with 0.02 moles. Limiting reagent is now our analyte, and now we're dealing with no acid left. We're dealing with 0.01 moles of strong base left, and we're dealing with 0.01 moles of the weak base conjugate. Now, another place where a lot of people get confused is, remember, if you have excess titrant, not your analyte, excess titrant, what you're adding to the solution, and it is in fact a strong base, therefore, this concentration is what determines your pH, not F minus. Remember, F minus Kb is so small that the dissociation is negligible compared to OH. So therefore, if we know the concentration of hydroxide after we have added too much, we know that it's 0.01 moles over volume total, which is 0.3 liters. Then we're dealing with a hydroxide concentration of 0.033, repeating, molar, and therefore, because we are dealing with a strong base, we do not have to deal with ice table or any equilibrium. Complete dissociation, POH is equal to negative log of 0.033. POH is equal to 1.48. Therefore, pH is equal to 12.52. Okay, and this is what we expect. An excess of a strong base in solution is going to ramp the pH up very quickly, very fast, very high. Okay, so now we are dealing with 12.52. So 11, 12, 13. 12.52 is roughly here. Now, this is a view of the titration curve. And remember, the titration curve for a weak base, a weak acid titrated with a strong base, has a curve that looks like that, right? The curve looks like that. We are seeing a not so sharp increase in the what we call buffering region, remember, but we are seeing an increase in what we call the area afterwards, right? So in this area, this is what we call the buffering region. And that's why we do not see as sharp of a spike with the amount of volume added. Here we see a very sharp spike with volume added because we are adding excess hydroxide ion. Okay, so this is the end of the acid titrated with a strong base. Next, we're going to look at a weak base titrated with strong acid and the calculations associated with that.